had the idea that just this is not
But it was a good shot anyway.
No, yeah, it was like,
Okay, so we're in section 17.2 on rigid body dynamics. So we're looking at an object whose shape matters. In fact, the point of application of the force is kind of important. Okay, so here the force acts over here, force acts over here, and so we are interested in finding the effect of moments due to these forces. So this happens to be an external moment, but those forces also produce a moment about this point is G. G is the center of mass, something which we found in the last class. So in general, for a rigid body, there are three equations. Now we are only looking at rigid bodies which are moving in the plane. By in the plane I mean they can translate along the x, y, and they can rotate up in the plane. So rotations are always about the z-axis or minus z-axis, which points out of the plane of the bird. So in that case, there are three equations. The first two equations are things we've written down in the past in chapter 13 when we looked at particles, when the shape of the object did not matter. The third equation is when you have a rigid body and when the point of application of the force is important, like the moment mg is the moment at g due to those forces and of course due to external moment. So the only new thing in this particular part of the course, rigid body dynamics, is that third equation. We've done the problems involving the first two. So in this lecture, we are going to look at a very special case of rigid body motion that involves no rotation, only translation. So the body is not rotating, it's only translating. When the body only translates and does not rotate, alpha is 0. When alpha is 0, what you can do is you can take these equations and rewrite them. The first two equations, fx, fy, do not change because acceleration doesn't show up. But the third equation will change. It's simply mg equals 0. That is the net moment. External moment about g is equal to 0. Cartesian is one way you want to do it. If things are moving in xy, if things are moving in sort of circles like a pendulum, you might want to use normal tangential. The only change is that now you resolve forces along n and t direction, use the acceleration in the nt coordinate, something which is in the formula sheet, also what we've done in the past, and go from there. The third equation is simply mg equals 0. Okay, so with that, let's see how to apply these formulas. Essentially, this section is about applying one of those two formulas, the left side or right side, depending on the problem. Okay, here is the first formula. Okay, so the jet aircraft has a total mass of 22 capital mg, which means it's 22 times 10 raised to 6 gram, which is 22,000 kilograms, right? And a center of mass at g, so that's given to you. Initially at takeoff, the engines provide a thrust 2t equals 4 kilonewtons and t prime 1.5 kilonewtons. Determine the acceleration, so that's one thing which is asked, of the plane and the normal reactions on the nose wheel and each of the two wing wheels located at B. So you got to find the reaction force at A, reaction force at B, and you got to find the acceleration. Acceleration, you like acceleration of G, the normal force at A, and normal force at B. Neglect the mass of the wheels and due to low velocity neglect any lift caused by the winds. Also, it's not been said here, but if friction is not given, nothing is mentioned about the friction, just assume it to be 0, there's no friction. So what distinguishes this particular problem from something we've done in chapter 13, which was quite a while back, is that the plane has a geometry and those forces are applied at a specific point with respect to g, which is the center of mass. We did not have dimensions in any of the problems we've done in chapter 13 on particles, okay, which introduces us, which makes us use the third equation which I talked about. So this is a case of pure translation because the plane is not rotating at this point, it's just translating along the horizontal. Okay, so let's write the equations of motion. Well, before that, obviously I have to draw a free body diagram. So you could draw the exact shape, but what really matters is that you draw the NA and B at approximately the right place. So NA and B two T and t prime. Okay, and the gravitational energy, or sorry, the weight of the plane will act through g. And if there was friction, clearly I would show the friction acting to the left, but there's no friction, so I would not draw the friction. So your free body diagram, like the free body diagram for um, particles, is very similar, except that you want to show the exact location. So it is not okay to draw, let's say, mg over here. If you draw mg over here, what will happen is your moment will be incorrect, because now you're showing mg over here. Mg is not acting here, but it's acting there. So the point of location is actually important in this case. Okay? Very common mistake. People draw mg wherever they want, and then they end up with wrong equations. So next is equations of motion. So in this case, you're better off trying to use Cartesian coordinates x, y, because the plane is going along the x, y axis. It's not like a pendulum where things are rotating about an axis. So equations of motion. There are three equations. Let's try the equation in the x direction. Fx equals mass times acceleration of g in the x direction. So net force is t prime plus 2t. Both of those are acting to the right in the positive x direction, equals mass times acceleration of g in the x direction. So t prime is 4 kilonewtons, so 4,000, plus 2t is 1,500 newtons, plus 2t, the whole thing, 2t is given to be 4 kilonewtons, so 4,000 equals the mass, which is 22,000 times agx. So that helps us to solve for the acceleration. It's simply, it comes out to be 0.25 meters per second squared. Okay, next let's write the equation of motion in the y direction. So Fy equals m ag in the y direction. So we see that the forces in the y direction are the normal force, which is acting upwards, so it's positive. The normal force at B, which is also positive. Mg is acting downwards, that's negative y direction, so minus mg, equals the acceleration of g in the y direction. Clearly, at this point, the plane is translating in the x direction. It's not taking off. It's not taking off yet. So acceleration in the y direction is 0.
Would it be 2NB, or would it just be once it gets 2 meters?
2nb. Yeah. So you could potentially write this as. You could also write it as 2na if you think of. Sorry, not. There's only one wheel in front. In the back, you could write 2nb. Well, in that case, you just distributed the forces. You could do that right now. You could do it later. I just keep it at nb, which is the net force on both the wheels, and then eventually you'll just divide by 2. That is assuming that they are equally distributed. So that's a fine detail. Okay, so in that equation, Na is unknown, Nb is unknown. And mg is known because we know the mass, we know gravity. So we cannot solve for Na and Nb at this point because there are 2 unknowns and we just have one equation. So we'll have to write the third equation, which is mg equals ig alpha. And in this case, we know that alpha is 0. So the net moment about g is equal to 0. Okay, so this is where we will use the free body diagram and the figure which is shown there to find the net force. Our convention is going to be any moment acting clockwise is negative, any moment acting counterclockwise is positive, just like we use for acceleration, right? So let's find the effect of each of those forces. Let's start with T prime. Okay, so T prime is acting here, G is down. So the way to find the effect of the moment is if you hold the object at G, which is the point about which I'm taking the moment, and apply the force at the point of interest, in which case it's going to be T prime. Will it cause a clockwise movement or a counterclockwise movement? So in this case, it's going to cause a clockwise movement. So that's going to be a negative moment, because it's counterclockwise, and we need to find the perpendicular distance from T prime to G. So we need to find that distance. So that's clearly 2.5 minus 1.2. 2.5 is the distance of T prime from the ground, and 1.2 is the distance of G from the ground. So if you want to find the distance from T, the application of T prime and G, it's going to be 2.5 minus 1.2. Okay. Similarly, next we find the moment due to 2t. Again, 2t is, since it's 2.3 meters from the ground and G is 1.2 meters from the ground, from the figure, you can see that 2t is going to cause a clockwise torque, because G is relatively below 2t. So it will cause a moment this way. So 2t times 2.3 minus 1.2, that's the magnitude. The sign is negative because clockwise moment. Okay, so we're done with two forces. mg will not cause any moment at G because mg acts at G. The moment arm is 0. So next, let's move to NB. Okay. NB is at a distance of 3 meters from G. So that's the perpendicular distance from the point of application of B and G. So NB times 3 is the moment. And again, if you hold the object at G and apply NB, it's also going to cause a clockwise torque or clockwise moment, so negative. The last force is NA. The distance from NA and the point G is 6 meters, so the moment is NA times 6. So again, if you hold the object at G and apply NA, it's going to cause a counterclockwise moment. A counterclockwise is positive. Okay, all that is equal to 0. Okay, so let's sub in the values for T prime and 2t. T prime is 1.5 times 10 raised to 3. 1.3 minus 2t is 4 times 10 raised to 3, or 4,000. It says 1,500. 4,000 times 1.1 minus 3NB plus 6NA equals 0. So from this we see that NA and NB are unknowns, everything else is known. This equation, let me write this as NA plus NB equals 22,000 times 9.81. So that's going to be our equation 1. This is equation 2. From equation 1 and 2, we see that there are two equations for two unknowns, NA and NB. So we can solve for those unknowns. So if you solve for NA and NB, get NA equals 73.38 kilonewtons and NB equals 140 142.44 kilonewtons.
That's each tire, is that each one?
That's the total one. The NB is what I've written down in my free body diagram. So if you want to find each of the forces on each of the tires in the rear, you'll have to divide that by half. So 71.22, 71.22. Yeah.
Where does the X and Y coordinates start? Like, why isn't the 6 in here? Because you have to move.
Say that again.
So, whenever you're finding like, where's the X and Y coordinates start? So where they would be negative.
So in this case, actually it doesn't matter where you put the origin of the xy. So the question is, where does that start? 0, 0 start. It really doesn't matter. You can put it, if you like, you can put it here or here. And the reason why I'm saying you can put it anywhere is because this distance is the distance from G to A. Right? So when we're looking at the distance between 2 points, it really doesn't matter. When you have the absolute position of points, like if you're interested in the absolute position of A, then yeah, we have to ask the question, where is the origin? Because depending on the origin, you'll have a different answer. So for a projectile motion, I think it matters, but for this motion, it does not matter where you put. But I think the direction is important, because then you'll have the wrong signs for things. Any other questions? Okay, so this is pretty much the recipe. You've got to first identify, it's a rigid body dynamics problem, which means you're going to be given the dimensions of the object, and the second thing is you apply those 3 equations. You'll have pretty much every single time you'll have either 2 equations, 2 unknowns, or 3 equations, 3 unknowns. Okay, so let's solve another problem in a similar flavor. A force P equals 300 newtons is applied to the 60 kilogram cart. Determine the reaction at both wheels at A and both wheels at B. So normal reaction at A, normal reaction at B, and the acceleration of the cart. Okay, let's start off with the free body diagram. Okay, so we've not been told anything about the friction, so just do not assume anything for the friction. Just assume there's no friction, so you don't have to put a force for friction. Okay, in this case again, same thing. We have to use the Cartesian coordinates to solve this problem, and it doesn't really matter where you put the coordinates, because we'll only look at relative distances, not absolute distances. So equations of motion. Fx equals mass times acceleration in the x direction. Okay, so all forces in the x direction. So the net force, external force, is P cosine 30 degrees. And since P is inclined that way, if you resolve it, it's going to be acting in the negative x direction. So it's negative equals mass times acceleration of g in the x direction. So minus 300 cosine 30 is 0.866 equals 60 times a g x. So we can solve for ag. The answer is negative 4.33 meters per second square. So that negative means that our assumed direction for acceleration of g was incorrect. We assume ag to be to the right in the positive x direction, but actually the acceleration is to the left. It does not mean deceleration, it just means it's going to the left. Which actually makes sense, right? If the force is applied to the left, it should move to the left. The next equation is Fy equals MAY. Okay, so now we have NA, which is upwards, so positive. NB, upwards, is positive. The force P is acting at an angle, so it's also going to contribute towards the Fy equation. The force in the y direction is going to be P sine of 30 degrees, and since that is upwards, if you resolve P in the vertical direction, it's upwards, it's going to be positive P minus mass times gravity acting downwards, so negative sign, equals the acceleration in the y direction. So the trolley or the crate doesn't take off, so the acceleration in the y direction should be 0. Okay, so NA plus NB plus 300 sine 30 is half minus 60 times 9.81 equals 0. So that is an equation with two unknowns, Na and Nb, and I cannot solve for those two using one equation. So I'll call that equation 1, and I'll wait for another equation to show up which I can use to solve for Na and Nb. So next, the last equation is the moment about g is 0 because the trolley does not rotate. So alpha is 0. So let's look at both the free body diagrams and the original figure to find the net moment at g. Okay, so from a free body diagram, there are 4 forces. Okay, so let's find the effect of moment due to all those effect of those 4 forces to give me the moment. So let's start with simple ones, Na and Nb. Na is acting upwards. So if you hold the object about g, where g is this point, then it will cause a moment equal to Na times the horizontal distance, or in this case the perpendicular distance, from A to G, which is 0.3. Okay? The second thing is that if you hold the object at G and you apply Na, it's going to create a clockwise torque, so negative. Next, Nb is at a distance of 0.2 from G, so the moment is 0.2. If you hold the object about G and apply the moment at force at Nb, then it's going to cause a counterclockwise torque, so positive. Okay, the third force, Mg, acts at G. The momentum is 0, so contribution is 0. The last force is P, and P acts at an angle. And so one way to find the moment due to P is to write P as a vector, Pi, whatever component in the I direction, component in the x direction and then find the distance of point of application from G and do it. An easier way, and which I would highly recommend, is think of P as two forces. One force is P cosine 30 acting to the left, and find the moment due to that force. Then the next is P sine 30 acting upwards, and then find the effect of that force. So you'll taking one force, creating two forces out of it, because one of them is in the x and y direction, and then it's easier to find the momentum because then you're only looking at the horizontal and vertical distance. So let's do it that way. Let me just put that in terms of an equation. Okay, so P, and feel free to write it on the free body diagram if you like. P sine 30, P cosine 30, and P sine 30 degrees, that's upwards and to the left. So P cosine 30 has a moment arm of basically this distance. So this distance is clearly from the figure you can see it is, what's that distance? Is 0.1. We are given 0.4 as the distance from this point to A, and we need to find it, and we know the distance from this level to here, so it's 0.4 minus 0.3, 0.1. So P cosine 30 degrees times 0.1, and so again the same thing. If hold the object at G and apply a force P that way, it will cause the object to, well, rotate counterclockwise if there was no other force, so positive. And then finally P sine 30 P sine 30 is this force. We need to find the distance from point P, where P is applied, to G, and we can see that that's 0.8 plus 0.3, so 0.38. So P sine 30 times 0.38. Okay, so hold the object at G. See the effect of P sine 30 is going to create a clockwise torque, so negative sign equals 0. Yeah.
Why did you put the very first one when you need so many forces in the X? Did you say P is 300?
You mean this equation?
Yeah.
Isn't it P something? Yeah,
Oh.
P is 300, I think. Yeah.
Oh, the one 900.
Oh, so
There was two.
yeah, there are two questions.
Alright.
Yeah, that question is you got to find the largest P. Okay, I didn't do that. I went to this one because this is straightforward. Yeah. My bad. I should have swapped them. So NA is unknown, NB is unknown, P is known, it's 300. So essentially we have the second equation. So from 1 and 2, we can solve for NA and NB. NA is 113.4 newtons. Okay, any questions? So it's really straightforward, right? You just first, if you identify it's a rigid body dynamics problem involving pure translation, and then setting up equations, and this is the level of complexity you can expect. Pretty much pretty much the same. The point of application of forces will differ based on the geometry and what application it is, but it's pretty much the same three questions will show up, the same three things will be asked. Of 100 kilograms, determine the acceleration of the cart and the normal reaction on the pair of wheels at A and B. Neglect the mass of the wheel. So clearly acceleration is straightforward. You just have to, let's do the, let me draw a free body diagram. 100. As I said, sometimes you're just better off writing the forces in the x and y direction. So in this case, I'm just going to write that down. It's 100 times 4/5, because this is a 345. What do you call three? The angle is such that it's 345 triangle, and this force down there is going to be 100 times 3/5. In other words, it's going to be 60. And this is going to be 80. So 80 is the force in the x direction, and 60 is the force in the y direction. Okay, again, x, y is the preferred coordinate frame. Acceleration is fx equals mass times agx. So that gives me 80 is the force in the x direction equals mass, which is 100 times agx. So clearly agx is 0.8. Okay, what I want you to do is I want you to solve for any n in B. So set up Fy equals mag y and moment g equals 0. So set up equations for Fy equals mag y. Clearly Fy is equal to 0 because the acceleration in the y direction is 0. Write the equation for mg and then solve for one of the two. Let's say solve for na and pull the answer. Okay, so do that. Okay, looks like I don't think there's enough time to solve it. So here's what I want you to do. Just put any answer and I'll give you credit for this. I'll finish the answer. I'll finish solving later on. But please post some answer. Okay, so I can give you credit for attempting. Well, I'll give you full points for that.
Does it fall off?